Hello ladies and gentlemen, and welcome back to another Geek Speech broadcast. As I promised previously, here is the lecture on the state space realization. Now if you remember this last slide from the previous lecture, I believe it was lecture introduction to control theory, we had the control signal, which was our acceleration. We had the speed with which, we basically influenced the speed directly with our acceleration, and then we had the space. And also we have here our prehistoric car walking between A and B. As long as we know the distance from the point we left and the speed, we know the state of the system as far as we are concerned. For this case, getting from A to B. U is the control steering, is the acceleration. We put more gas or less gas. And S, the space, reaching the final destination. This is the output that we are interested in. And we also drew this diagram that with the control signal we hit the state and we get an output. And the thing is, the whole signal, remember this is a signal, this is across the whole time. The way we wiggle our input, our control signal, we can either minimize the fuel, minimize the time in which we reach our destination. This is what a control problem is all about. And I promised you a way to formalize this. Okay, now in order to be able to formalize this, we have to start from somewhere, right? We need to have an initial state. This is very important. So we are just going to start from, so this is my state. So my state is actually a vector. So x is a vector which has x1 and x2, which is S and V. x0 equals 0, 0. So initially I start from point A with speed A. I am not moving. The initial state of the system is 0, 0. Good, so I have a starting point. Now I need to describe the change of the state. So how do I describe the change of the state? I'm sorry guys, it's derivatives. It's all around us. We cannot get away from them. So x dot equals, I'm going to write it directly, ax plus bu. So this is the equation that describes any linear system. Okay, so I've introduced two terms. One is this equation, and there will be another one, and two, linear system. Okay, so I'm going to start with two. What is a linear system? So let's say that x is the state variable, so x, the change of x, equals f of x. So a linear system is a system where f of x is linear. Attention, f of x, so f of x equals ax plus b is actually not a linear function. Well, it is a linear function if b is 0, but this is not a linear function. This is stupid. Linear function is a function for which we have f of x plus y equals f of x plus f of y, and, very important, two conditions, f of alpha x, where alpha is a scalar, equals alpha f of x, where x and y are vectors. Now, if you don't know linear algebra, if you don't know vectors, this is not for you anyway, so you're not watching this lecture anyways. But I'm basically writing all these variables in a column, and yeah, that's a fancy way of working with many variables at once. And it actually simplifies things a lot when we analyze. If we get here a matrix, here a vector, here a matrix, here a vector. So this is what linear system is. Now if it's linear, we can actually write it in this form. So there is a matrix A multiplied by the current state of the system, so the change, the way it evolves from this state. So I am at state 1, say state 1, and I'm going towards another state. The change in the state, so this thing over here, delta state or whatever, depends on the initial state, which is this x, and also depends on our control input. So this is how we influence. So the natural physics of the system would be the change of the system equals a of x if it's a linear system. If it's not a linear system, it can be linearized, but let's worry now about linear system. I mean, trust me, most of the systems can be written in this form. This is not the point. Where I'm going is just it's most of the systems are not linear, but most of them can be linearized around the point of interest. Okay, so the change, this is actually quite logical, equals something or the initial state plus something or the input. So this is how you memorize this equation. How you, of course, you don't need to memorize. You need to just wake up at night and just say x derived equals ax plus bu. But this is the state, but we are actually interested in the output, which is y. So y equals c of x. Okay, so the state is physical, is there. Y is something that we derive from the state. In our case, for example, we have the state which is s and v. Our output is only s. So you can imagine that here we can have s equals c multiplied by s v. So c should be something like 1, 0. Right, because we get 1 multiplied by s plus 0 multiplied by v. It depends on s, it doesn't depend on v. So this is trivial. Good. So now let's see how we can describe this. I mean, how do we find, basically every system can be described through A, B, and C. So once we have found the A, B, and C matrices, we have the whole complexity of the system hidden or embedded or squished into these matrices. If we have many variables here, many state variables, of course this is A is going to be larger. If we want to control more things, I need a bigger B matrix. If I am interested in more things at the output, I'm looking also at the engine temperature, I will need to worry about a bigger C matrix. So now let's just flip the slide and come back to our system. So our system was pretty easy, going from A to B, with you know, at each point in time we had the space and the speed, and we could be able to control the acceleration. So this was the state, this was the control, and the only thing that we know is that A equals S, right? And S is the output. So let's formalize this a bit. How do we formalize? First of all, the state X is equal to x1, x2. x1, let it be S. x2 equals V equals, right? This is what we know. Therefore, it means that x2 equals x1 derived. This is very important. Good. Now, this is all there is to this system, apart from the initial conditions. So we could start from a very high speed, and if we wiggle our input signal, we can get past our girlfriend's house. We can start going backwards, and if we wiggle our input signal, the acceleration, we can never reach our girlfriend's house. If we start from 0, 0 and wiggle our input signal, we will get exactly to the girlfriend's house. But the thing is, the way we hit the physics of the system, the space and the speed with the acceleration, is the same, is described by this mega difficult differential equation here. The acceleration is the double derivative of space. Good. And now we need to write, right? We need to put the system in a form like ax plus bu. Right now, this is like weird how to do. So I'm just gonna write component by component. X1 derived, x2 derived equals a multiplied by, I'm just gonna put, so what do I expect here? I expect the matrix multiplied by x1 x2, right? Plus, what do I expect here? Now this is difficult since I have two lines here, two lines here. I expect here also two lines multiplied by u. U is a scalar. We are only controlling one thing, the acceleration. Now let's look at x1 derived, right? X1 derived, what is it? X1 derived, it's actually x2, right? So we need to express everything in regard to either the states or the control signal. X2 derived equals what? X2 derived equals space twice derived equals actually the control signal. So now we are good, because x1 derived equals x2. It means that here I have 0 multiplied by x1 plus 1 multiplied by x2 plus, is there any u here? No. So I put a 0 here. Then x2 derived equals x2 dot, I'm sorry, I will not use derived anymore. x2 dot equals, it does not depend on x1, it does not depend on x2, so it equals 0 0, and then it depends once on u. So this is how the change in the state of the system depends on the state plus the control signal. As you can see here, what is a very interesting thing that we can already feel. So let's say I do not know about the car, I do not know about the road, I only see this equation, right? So somebody tells me, hey, this is your system, these are the states, this is the first equation in the state space representation. Well, you can already tell from this 0 1 here, if I have 0 here, it means that the change in x1, right, is not affected by u. So u does not affect x1 directly. U affects x2 directly. But then again, the change in x1, it does depend on x2, because we have 1 here. So actually u first hits x2 and then x2 hits x1. So with the control signal, I'm actually controlling both x1 and x2. So I'm really being very, I don't know, very efficient, because if I had like a system where my control signal would only hit x2 and x1 would not depend, the change in x1 will not depend on x2 at all, then it would be bad, because I will never be able to control x1, right? Good. And now I'm going to write also the equation for the output. So y equals matrix here multiplied by the state x1 x2. Now since it is only scalar, I only need one line, because it's this multiplied by this, and I get a scalar and I'm a happy man. And x1 is the space, y is the space, so it only depends on x1 and on 0. So as you can see, we are not interested what happens with x2. We can reach our girlfriend's house with 100 kilometers per hour or with 0. Although in a real life's problem, we would like to reach there with 0 speed. So we would also be interested in the speed, because we would like to be there and stop there. As you can see, it's non-trivial for a robot, because if a robot reaches there and he doesn't have he doesn't have speed 0, it cannot stop like instantly. It has to have speed 0 when it reaches the house. So this is my state space realization here, these two equations. First equation and second equation. So only by looking at this equation, I don't even need to know, I don't even need to worry about this. If I can, for example, get y to be y at time t can be, I don't know, the distance, which is 100 miles. That's all I need to know. I don't even need to know the initial physical data of the problem. I just need this and that. Okay, so this is the state space realization, and that should end today's lecture. But I should continue on with the state space realization, but I won't do that because in your undergraduate studies you probably didn't do too much of a state space realization. They just told you about it a bit, and yeah, they should have told you more. But I will go on with the classical control theory, which what so this thing was not first. This came second, but this is the most logical, and this is how you can feel it, because you have some initial conditions and you have some differential equations that told you, okay, I start from there and this is how the change goes on, and then I go to another state and this is how it changes from that state, and then I go to the other state and this is how it changes from that change. And u again is like a signal from, I don't know, 0 to infinity. It's not a number again. Okay, and people, what did they do when they saw these differential equations? So they actually started from here, from the implicit description of the system, and they said, hey, we do not like a differential equation, let's use Laplace transform. Okay, so let's use Laplace transform. So what does Laplace transform do? So I'm making a connection with the next lecture. Laplace transform takes one signal defined over, let's say, the bilateral Laplace transform. I will talk in detail about the Laplace transform next time, don't worry about it, and squishes it. It squishes it into something of the form, let's say f of s, say big F of s. So the Laplace transform is, if I have f of t defined on this large interval, the Laplace transform is, the bilateral Laplace transform is minus infinity plus infinity integral over f of t e to the minus st dt. So as you can see, this integral takes all the information in f of t over minus infinity plus infinity, squishes it and you know, attaches it to an s variable, which we don't know what it means, but I will tell you now. It's a complex variable, and for those of you familiar with the Fourier transform, I will tell you even more later in the next lecture where does this s come from and how you can use it. But the main point here is that if the initial conditions are 0, so if initial conditions zero, then Laplace from x dot equals s x dot of t. So we go from the time domain to this thing called the s domain, complex domain, whatever domain. It's an abstract thing, it doesn't exist in reality, it's only a tool to work with. So condition 0 means x of 0 equals 0. So if you can imagine, we had there we had that space twice derived equals acceleration, yeah. So we have that y, which is our output, twice derived equals our control signal, which is actually our input. Remember, always have this in mind, u x y. And if we apply Laplace transform and we assume that everything is 0 and nice, we get s squared. For each dot I get an s, y of s equals u of s. And then I can say that y of s divided by u of s, which in your classes you have called this g of s, equals 1 over s squared. But again, here I only deal with the change, you know, how my control input changes. it does not deal with the initial conditions. I do not know exactly what my system is doing. I'm just telling how it behaves if the initial conditions were 0. Okay, and you might say that so why, if I told you this, I mean, this seems easy, but what is 1 over s squared when I am going to reach my girlfriend's house? Do I know when I'm going to reach my girlfriend's house? No, I don't. I mean, what is this 1 over s squared? Whereas here, I knew that I start from x of 0, x1, x2, 0, 0. This is the change, so I know at time 1, time 2, time 3, time 4, time 5, maybe at time 8, just following the changes and the function, I would be at my girlfriend's house. Here, it's only concerned with the change. I do not know where I am. It's just, let's say, qualitatively analyzing the dynamics of the system. And this, we can actually reach this form from our very logic state space representation. So if you remember our state space equations, we got like x equals ax plus bu, and we got something like y equals cx, right? So I can apply Laplace transform from this for this, and I get sx of s, whatever, I'm not going to write it again, equals a x of s, I'm not going to write it again, plus bu of s, I'm not going to write it again. Now I have here s, usually I have here s minus a, right, multiplied by x, but this is a scalar, this is a matrix, so I cannot do that. I have to multiply by the unity matrix equals bu, right? And from here I get that x, assuming si minus a is invertible, I get si minus a to the power of minus 1 bu. And then when I insert it in this equation, I get that y equals c s y minus a to the power of minus 1 bu. So this is actually my g of s. So if I am smart enough and get the state space representation, the g of s is immediate. C s y minus a minus 1 b. This is my g of s. So you can see it's immediate from the state space representation to the transfer function. It's immediate. So state space is better, but now I will deal with the transfer functions and with this highly mathematical abstractization. But I just wanted you to see where it comes from. It comes from physics. So again, physics of the system. Okay, physics. I need to write down here, which goes to differential equations, which can be written in state space form, for which I get the transfer function. I can go either like this, or I can go right directly like this. But in state space form, I'm working in time domain with differential equations and initial conditions, whereas with transfer functions, I'm working in S domain, in Laplace domain. Laplace, which is something abstract, not real, and it's highly mathematical, and it's hard to see how am I going to control, how am I going to achieve stuff in real life with this transfer functions. However, this is what you are taught in school, this is what you need to learn, and this can also be very exciting. So I'm just going to tell you next lecture about Laplace transformation, and hopefully we'll have a great time also with these transfer functions. Okay, see you guys next time.